Today's lesson's over section 4.3, where we'll be talking about derivatives and the shapes of curves. Now, first thing we want to kind of talk about is the mean value theorem. It says that let f be a differentiable function on a closed interval between a and b. If that's the case, then there exists a number c on that curve or on that interval such that the derivative, or there is a derivative of c that is equal to the slope between a and b. So that means that if an object is moving according to the continuous function on a given time interval, the object must at least one time on that interval between a and b have an instantaneous velocity, so a derivative, equal to the average velocity on a and b. So it's really just like looking at the two endpoints, the slope between them, there has to be a derivative slope that is equal to that slope. So the main thing we'll be doing in this section is something called curve analysis. So we'll be looking at the first and second derivatives of our function and using those to be able to take out characteristics of the function and be able to use that to sketch our graph. So remember that intervals of increasing decreasing is when the derivative is positive, that means your interval is increasing. When your derivative is negative, that means your function is decreasing. The first derivative test also tells us that let c be a critical number on the continuous function. If the derivative is changing from positive to negative, that means there's a local max. If it's going from negative to positive, that means there's a local min. And then also, if there's no change, that means there's no extrema there. Also, we'll talk about concavity. Remember that concavity refers to the second derivative. And so if I'm taking the second derivative of a function and it's positive, that means it's concave up in that area. If it's the second derivative is negative, that means it's concave down. Also, the points where it does equal 0, those would be points of inflection. And so those are critical points is when they change from up to down or down to up. Okay, so let's go ahead and try one of these examples. So I'm given the equation y equals x to the fourth minus 4x cubed. And so first we kind of want to understand if there's anything else going on here. So the domain for this function is all reals. There's no asymptotes in this. So I first want to figure out where my zeros are. So I'm going to set the entire function equal to 0 and solve. So I find that it's 0 and 4. So that's where it's going to cross the x-axis. Okay. And from there, I want to be able to find the intervals of increasing and decreasing, which means I need to take the first derivative of my function, which gives me 4x cubed minus 12x squared. I want to set that equal to 0, because that'll allow me to find my critical numbers for my function as well. And so solving, that allows me to find that it's 0 and 3. So, and it's okay for these things to be multiple places. So see that 0 is 0, 0, and it's also going to be one of our critical numbers. That's okay. So when I'm testing this, I want to look in between those critical numbers to see what my function is doing for its slope. And so I plug in just some values in between. I just pick -1 on the left side of 0, 1 in the middle between 0 and 3, and 4 on the right of 3. I plug those in and find that in between, or on the left side of 0 it's negative, in between 0 and 3 it's negative, and on the right side of 3 it's positive. So that means that it's increasing from 3 to infinity, it's decreasing from -1 to 0, and from 0 to 3. And so because it's negative to positive by 3, that means that that will be a minimum, because it's decreasing and then it's starting to increase. So that's going to be one of your local mins for that. We also want to know what those points are. So obviously f of 0 is 0. Plugging in 3 gets me -27. So that'll be a local min for me. Okay. Now I want to be able to move on to the second derivative and look at concavity. So then I take my first derivative and then take the second derivative of that. So that gets me 12x squared minus 24x. I'm going to set that equal to 0 because that'll allow me to find any points of inflection that I need to reference. And so that allows me to see that, oh, x equals 0 again, and x equals 2 here. So I'll do the same thing I did with the first derivative. I'm going to look in between. So I'm picking values on the left side of 0, which is -1, in between 0 and 2, which is 1, and then on the right side of 2, which is 3. And so then I see that the left side of 0, it's positive. In between 0 and 2, it's negative. And on the right side of 2, it's positive. So that means that it's going to be concave up from -infinity to 0 and from 2 to infinity. It's also going to be concave down between 0 and 2. We have a point of inflection at 2. And so I want to be able to find that. So kind of like what we did with the local mins and local maxes, I plug in those critical numbers into my original function to find out what my y value should be. So obviously f of 0 is 0. We already found that. F of 2 here will get me 2 to the 4th minus 4 times 2 cubed, which should be -16. And so now I have all my information. I first want to plug in my points, or plot my points, onto the graph. So 0, 0, and then my 2, -16. I kind of want to label these because they're going to be pretty far apart. 3, comma, -27, that's my local min. And I also have another 0 at 4, 0. And so using that, I'm able to kind of finish the picture using my concavity and my increasing and decreasing stuff. And there you go. Example 2, I have the function of e to the 1 divided by x power. Now this one's unique in the sense that you're not really going to have a lot of critical points here because when I set e to the 1 over x power equal to 0 and try to solve, I get ln of 0 on one side, which is not possible. Also means that I get 1 over x, so at 0, that's undefined. So I have an asymptote, and so my domain is kind of restricted, so I can't get 0 because of that. So I'm able to get that kind of information to begin with. So I have no zeros, nothing that crosses the x-axis. And then from there I want to take the first derivative so I can look at my increasing and decreasing stuff. Here once again I get the same idea, asymptote at 0. I try to do my thing again, but it's the same equation, so it's not possible. So there are no mins or maxes on this one. Now, because 0 is an asymptote, that means we can change from increasing to decreasing, so I kind of want to check that out. So I'll plug in -1 into my function. I'll also plug in 1 into our function to kind of see what we get. We get -1 over e. That means we're negative to the left side of 0. Plugging in 1 will get us -e to the first, which is also negative. So your function is decreasing at all times except for 0. So -infinity to 0 and 0 to infinity. So that's good information to have. Now I want to be able to find concavity of this. So I'm going to take the second derivative. Now to make this a little easier, I'm going to use it in the form of with the -x squared to the -2nd power up there rather than with it in division, just so I can just use the product rule rather than the quotient rule. And so I'll take the derivative of the first, which is going to be, now notice there's a negative out front, and so when I bring down the -2, that cancels out that negative. And then remember that e to itself is always e. Here I can factor out an e to the 1 divided by x power out of everything. And so I can kind of simplify this. They have not quite like denominators, so I'm going to make them common. So it gives me a 2x plus 1 over x to the 4th, and then put it all together as one kind of function. then from there, I'll do the same thing that I did with the other one. So I'll set it equals 0. Notice that x to the fourth is still an asymptote, so I can kind of ignore that. Set my top or my numerators equal to 0. Remember that e to the 1 over x equals 0 is not possible, but I do have a point of inflection at -1/2. So using that and 0, where my asymptote is, I'm going to plug in points in those same regions and figure out whether I'm positive or negative in those, so I can figure out my concavity. And so for f of double prime of -1, I get -1 over e, so it's negative to the left side of -1/2. And then in between -1/2 and 0, I get the following thing. So notice I have 1/2 over 1 over 256. I can flip that up and multiply those two numbers together. It gets me 128, but then the e moves down. But overall, that's a positive number. So in between -1/2 and 0, it's concave up. And then from on the right side of 0, it's also positive with 3 times e to the first. So I know my concavity. Here we do have a point of inflection. So for point of inflections, anytime you change from either negative to positive or positive to negative, that means you're changing concavity, so therefore there's a point of inflection. If we stay like negative to negative or positive to positive, we don't really have a point of inflection, kind of like our asymptote at 0. Okay, so now once I have all that good stuff, I'm able to start graphing. Now this one's kind of curious, is that -1/2, we have that one point, so it's concave down to that point, but then concave up. We have an asymptote, but it kind of, like if you plug in values approaching, the numbers are so small when they get to 0 that it doesn't like go up to infinity or negative infinity. It actually approaches 0, so that's why there's an open circle there. Then on the other side, it's just concave up, but it never crosses the x-axis, so it kind of just looks like that. Okay? Well, thanks for watching. Have fun.